Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to finish up our unit on exponents by talking about exponential functions. So let's just hop right into it. Let's look at this introductory problem to get us started. It says a king gave his subjects a hypothetical question to ponder as he decided which one of them he was going to make, quote, hand of the king, unquote. The question was as follows. Suppose I gave each of you 10 silver coins. You have the option of getting an additional 1,000 coins each day for the next 30 days, or I will double the total of your coins every day, again for the next 30 days. Which would you choose and why? So take a moment, pause the video, and think about which option you would prefer based on what you think would give you the most coins at the end of 30 days. So if you chose the 1,000 coins each day, well, you start off with 10 coins, and then for 30 days, you're getting 1,000 coins a day. So you end up with 30,000 plus your initial 10. So we'll call that option A. Option A, you'll have 30,010 coins. Seems like a good amount, right? Well, let's think about option B. Option B is not as easy to figure out, right? All we know is that we double the amount of coins each day. One thing you could do would be to make a little t-chart. So number of days and actually I'm going to need more space here. Number of days, number of coins. So after 0 days, right, you have 10 coins because you start off with 10. Well, after 1 day, you're going to have 20 coins because he's going to double it on the first day. Second day, you have 40. Third day, you have 80. And you can see how we just keep doubling, right? Well, let's see. By day, we'll go up to day 10. Might have to come over here. So after 10 days, you have 10,240 coins. And actually, right around 10 days is when you have about the same amount with both options, right? If you were doing option A, well, after 10 days, you'd have 10,000 coins plus your additional 10. So 10,010 coins. So it seems like they're about even at 10 days. Well, now though, if you keep going and you do the next 10 days, you're going to see that option B, the number of coins starts to grow very, very quickly. And it's already growing quickly, right, from day 0 to day 10, because it is doubling. It's just it doesn't seem like a big amount, right, because for option A, you're getting 1,000 coins each day. And you can see, up until day 7, right? From day 0 to 6, you don't even have 1,000 coins from option B. But let's think about it. So day 11, you have 20,480. After day 12, you have 40,960. So after day 12, you already have more coins than you'll ever have from option A. Right? The most you'll get from option A after 30 days is 30,010 coins. Well, after 12 days of option B, you've already surpassed that by over 10,000 coins, and we're not even halfway done. Turns out if you go for all 30 days here and you keep doubling your amount of coins, you get a very, 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 very large number. And we're not even going to put it on the screen because it's so big. Actually, I will put the final answer on the screen for option B. And that is going to be 10,737,418,240 coins. So it would actually be a huge loss to go with option A over option B. Even though option A seems like it's a lot, right? You get 30,000. Well, 30,000 is nothing compared to 10 billion. So this is an example of the difference between linear growth and exponential growth. Linear growth or linear functions have what we call a constant slope, right? They just grow by the same amount for every x value that we increase by. In this case, we could think of our x values as days. So for each day, our function grew by 1,000 coins. For exponential growth, though, our function didn't grow by the same amount each day. It got multiplied by a certain number each day, that number being 2. So you can see that, multiplying by a number can sometimes make the function grow by a whole lot more than just adding the same amount each day. So this is the difference between linear and exponential growth. Let's keep going. Specifically get into what exponential functions are. So previously, we've only worked in depth with linear functions. Like I said, these are not the only types of functions that model things in the real world. For the next few lessons, we are going to focus on a new group of functions, exponential functions. And we're actually just going to squeeze this lesson all into one. Maybe it'll be more than one video because there's a lot, but still just be one lesson. These have different forms than linear functions and behave quite differently. Let me switch that. Should be than linear functions. We will explore what their graphs look like, how their equations are set up, and when to choose them over a linear function model. So let's first get a visual of what an exponential function looks like. So on this first graph, we're going to draw option 1 or option A. This is where we added 1,000 coins each day. Down on the graph below, we are going to sketch what option 2 would look like, where we double the amount of coins every day. So here's where I'd like you to pause the video, sketch a graph for what option A would look like, and you only need to go up to, we'll say 10 days. For option 2, again, we'll also only go up to 10 days, because after that, it's going to start going off the charts. So for each option, go through 10 days, and that'll give us an idea of what each graph looks like. Okay, so I'm actually going to put them on the same graph because otherwise I'd have to scroll back and forth and I'd lose one when I go to the next. So for my linear function, right at day 0, I start with 10 coins. Right, I get 10 coins to start. Then after day 1, I add 1,000, so I get 1,010, and I just keep going. So this is going to look like a nice line. You get something that looks like this. And to be fair, I should cut this off at 0 because we're not going into the negative numbers. So it just looks like that. Now my exponential function looks a little different, right? We said we start with 10 again. I'll do this one in, let's do green. So I still start with 10, so they start at the same spot. But after one day, I only have 20. After the next day, I have 40, then 80, then 160, then 320, then 640, then 1280, then we have 2560. I'm just making guesses about where these points are going. Then I have 5,120. And then on day 10, I have 10,240. So this is what the shape of this exponential function is going to look like. So you can see that for these first few days, right, it doesn't look like this exponential function is doing much, right? But once those numbers start to increase, when you double those numbers, they get rather large very, very quickly. So again, for the first 10 days, we end up with about the same between linear and exponential growth. But after those first 10 days, that is where the exponential function, the green function, starts taking off and grows, or the number, the y values for the green function are getting larger at a much quicker rate than the y values for the pink. So again, green, exponential function, pink, linear function. Again, we've worked with linear before, so exponential is the new one for today. On the page below, we're going to look at some similarities and differences between the two functions. So think about as many of these that you can think of. Think about as many things that are similar about the functions. Think of as many things that are different about them, and just jot them down in these blanks below, and then we'll have a discussion. Okay, so I'm just going to keep the picture up here so we can kind of discuss as we write things down. As far as similarities go, so we'll do similarities over here. Well, they both have a y-intercept. Both have a y-intercept because they both start off at y equals 10. Right? That's our y-intercept. Both functions are increasing, right? The y values are getting larger. They're getting more positive in both functions. So both functions are increasing. That's another similarity. Now we need to talk about the differences. Well, I think one of the biggest differences is, right, one is a line while one is curved. And there's many different ways of writing that out, right? Maybe you said one has a constant slope and one has a slope that's changing. Right? If I look at the beginning of this function, right, the slope it's positive, but it's not very large, right? But if I look at this part of the function, the slope is getting more steep. A little bit of a calculus thing, if you guys take that in a couple of years. Essentially, to think about slope, we can draw a tangent line to the graph. Again, the calculus concept, so don't worry too much about it if you don't understand it. But if I'm trying to find the slope, I'm going to draw a line that's tangent to the graph. So the slope at this point looks like this lime green line. That would be the slope. But if I look at the slope at this point, right, that tangent line is much more steep than it was at x equals 3. Right? The slope at x equals 9 for the dark green function is more steep, more positive than it is at x equals 3. Now, if I think about the slope for this pink line, right, well, it doesn't matter where I draw this tangent line. At all of these points, the tangent line is going to look the same. So the slope is always the same. But with an exponential function, because it's curved, those tangent lines they will all be different they will all be different based on the x value that you're drawing that tangent line to. So again, a little bit of a calculus concept, just showing you, why that slope is different at different spots of the dark green function. So if you had said something like the slope is different for the dark green, that would also be acceptable. Maybe you said the pink function straight while the other one is curved. That's also acceptable, right? We're just looking for differences. So these are kind of the visual differences. Now we're going to look at what the equation of an exponential function looks like. So let's jump down to this part. And here we have the standard form for an exponential equation. So just like we had general forms for linear equations, like y equals mx plus b, right? We had several different forms. We had y equals mx plus b. We had y minus y1 equal to m times the quantity x minus x1. And we even had a standard form, ax plus by equals c. These were all linear equations, right? Well, now we have standard form for an exponential equation. And what we're going to realize is that these letters right here don't always stand for what they did in linear equations. So here's what I mean. The standard form for an exponential equation is y equals a times b to the x. Well, a actually represents the y-intercept here, or what we call the initial value. It's important to note that a will not be 0. Now, you can have exponential functions where the y-intercept is 0. We're not going to look at those in this class, though. So we're going to take a very basic approach to exponential functions by just working with an equation that looks like this, and the a will never be 0 here. And you can think about it, if I made the a 0, so if it was y equals 0 times b to the x, well, then my function is always going to be 0, right? Because 0 times anything is going to be 0. So if my a was 0, I would just have a constant function, and, well, here's what it would look like. If my y value was always 0, well, then my function would look like this. It would just be a horizontal line that is the x-axis. So a is not going to be 0, not if we have an exponential function. The b represents the constant ratio. If we think back to our Keenan his subjects example, well, the constant ratio for option B was 2 because we were doubling the amount of coins we got each day. Your constant ratio is what you're multiplying by for each new x value. Right? So again, our example above, we multiplied by 2 each day. But you could multiply by 4 each day. You could multiply by 5.5. You could even multiply by 1/2 or 2/3. The only numbers that b cannot be are negative numbers. So b has to be greater than 0. And b can also not be 1. And there's some reasons for that. You may want to think through, why b has to be greater than 0, why b cannot be 1. But I encourage you to think through those on your own. For now, we're just going to keep going and move forward with these rules that, b has to be a positive number that is not equal to 1. So let's go through and look at how these equations affect graphs. So here are the exponential functions we're going to try to graph. I only need you to graph these for x values 0 to 4. So 0, 1, 2, 3, and 4. And then you'll connect your points. You'll remember for a line, you only needed 2 points to accurately graph your function. For an exponential function, it's a little different, right? You may not get the entire picture just from 2 points because our function is going to be curved. So we're going to graph more than just 2 so you get an accurate idea of what it looks like. So let's break down the first one, and then you can try the second one on your own. So for the first one, we think back to our standard form, y equals a times b to the x. Well, a is our initial value, right, or our y-intercept. Here, our y-intercept is 5. So that's the first point I can graph. 5 right on the y-axis. Now, I need to figure out what y is when x is equal to 1, 2, 3, and 4. Well, I can just do that with a table, right? Here's x values, here's y values. We know that when x is 0, y is 5, because that's our y-intercept. When x is 1, well, I'm going to get y equals 5 times 2 to the power of 1. That gives me, that gives me 5 times 2, which gives me 10. So when x is equal to 1, y is equal to 10. I can do the same thing when x is equal to 2. Going to get y is equal to 5 times 2 to the power of 2, or 5 times 4, which gives me 20. So y is equal to 20. And you'll notice a pattern here. If you do the math, when x is equal to 3, y is equal to 40. When x is equal to 4, y is equal to 80. And again, that's because we are multiplying by that constant ratio. In this case, the constant ratio is 2. We're multiplying by 2 every time. So now I'm going to graph the rest of these points. Again, you can pause the video at any time to look at the math again. When x is 1, y is 10. When x is, y is 10. When x is 2, y is 20. X is 3, y is 40. X is 4, y is 80. So our function looks like this. And to be fair, this would actually continue this way. We're not doing a word problem where, numbers can't be negative. So our function would continue off to the left like that. It is important to note that while the function does continue to the left, and I'm just extending the x-axis here, our function would never cross the x-axis. So it goes, if we're looking at it going this way, the y values are getting smaller and smaller and smaller, but they never quite reach 0. Okay, they get to it approaches 0, but it never quite gets to 0. And you could think about why. Well, if you take a look at this equation right here, is there a number you could substitute in for x that would make your y equal to 0? And you could test any type of number. You could test negative numbers. You could test 0. You could test positive numbers. You could test fractions, etc. And you could just punch them into your calculator. You don't have to work them all by hand. But there's no x value that you could substitute into your equation to get a negative y value. There's also no x value you could substitute in to get 0. So all of the y values here are positive, which means our function is going to lie completely above the x-axis. There are some functions, some exponential functions that are below the x-axis, but we'll get to those later. Just thinking about this function, right, there's no x values you could substitute in that would give you a y value that's negative. Let's look at the function on the right. You can call this a function or an equation. It's both. It's not written in function form, but it still acts like a function. There's inputs, our x values, and there's outputs, which are our y values. So make a t-chart for your x and your y's, then graph these points, connect them, and see what the function looks like. All right, so our initial value was 2, and then our function grew by a factor of 3 each time. So when x was equal to 1, y was equal to 6, x was equal to 2, y was equal to 18, etc. And you can see that this purple function looks like it gets steeper a little bit more quickly than the red function does. And it does that because this constant ratio was larger than the one for the red. So this function was growing more quickly than the red function was. And again, same thing here. There's no x value that you could substitute in to get 0 or negative number for the y's. That's why the purple function will lie completely above the x-axis. Okay, let's do one where our constant ratio is a fraction and not a whole number. Same thing though, I want you to try both of these on your own. You'll notice that both of these are going to look a little different, not only from each other, right? They're not going to look the same. They're also going to look different from the two graphs up above. But you can still do them the same way, still have your x and y t-chart, and then use those points to graph. So pause the video, attempt it on your own, and then you can come back and see if you were correct. All right, so you'll notice that for the orange, our function's actually decreasing here. And that's because our constant ratio is a fraction. So if I'm multiplying by 1/2 each time, Well, that's going to make my y values decrease in this case, because I started off with positive 32, and if I multiply by 1/2, my y values are going to get closer and closer to 0, because I'm cutting them in half every time. For green, my constant ratio is also a fraction, which means my y values, they're not decreasing, but they are still getting closer and closer to 0 each time, right? Our y values, as we move further along the x-axis, my y values are approaching 0. So here's something to pick up on, right? If our constant ratio is a number greater than 1, right? So up above we had constant ratios of 2 and 3. Our function's going to be getting farther and farther away from 0, right? Our function was going up towards infinity for both of those. Well, if our constant ratios are between 0 and 1, so they're fractions between 0 and 1, then our exponential function is going to be getting closer and closer to 0 as we move further and further to the right along the x-axis. So those are some patterns you can pick up on, and you'll pick up on them more as we do more and more examples. Okay, I think we are going to pause the video here. You know what, let's fill in these conclusions though, and then we will pause and we'll make a part 2 for the rest of this lesson. So what we just kind of talked about, if the constant ratio is greater than 1, then the function moves farther away from the x-axis. It can go to positive or negative infinity. So it's going to move away from 0. It's going to get really, really large in the positive direction, or really, really small, or really, really large in the negative direction. If the constant ratio is between 0 and 1, then the function moves closer, and we can say approaches 0. So regardless of whether the function's above or below the x-axis, it's going to be getting closer and closer to 0 if our constant ratio is a fraction between 0 and 1. Finally, the initial value was always our y-intercept. So again, that's a good starting spot, and then you can go off from there. We are going to stop there, and we will come back and make a part 2 for going the other way. So if we're given a function, if we're given a graph, can we write the actual function? Or maybe if we're given a table, can we write the actual function? So in this video, we learned how to graph. Next video, we'll learn how to write the algebraic form of the function. All right, as always, enjoy the rest of your day, and we will look forward to seeing you next time.